Good morning, my name is Estefania Coronado and I am with the I2CAT Foundation in Spain, and today I'm going to present a work entitled Delay-Sensitive Wireless Content Delivery and Interpretable Artificial Intelligence Approach that we have performed jointly with the University of Castilla-La Mancha in Spain and the Politecnica University of Marche in Italy. I will divide my presentation into 5 big blocks. So first I will introduce the context and the motivation. In the second place, I will define what we mean by interpretable and explainable artificial intelligence and the requirements of this interpretable artificial intelligence with respect to wireless networks. Later on, based on these requirements, I will introduce a predictive scheme based on ML models for AI-based channel access optimization in Wi-Fi networks. And finally, I will discuss the results of the performance evaluation and provide some concluding remarks and future works. There is no doubt that the last 2 years have been completely different in the entire world. So we have made our homes the center of our lives, and it has been our workplace, our place for learning, it has been our place for the free time, and many of these activities have involved the consumption of delay-sensitive traffic that is characterized by high bit rate and or low latency, and that have been consumed especially in cellular and wireless networks. One of these scenarios that I've mentioned is actually the one related to the education system. Although of course we initially started from an online educational system given the situation, little by little we moved to hybrid modes that allow safe learning at the same time that allow also interaction between people, between students and professors. And one of the form of these hybrid modes is the one that we can see in the slide on the right, where we can see that the teacher or the professor is in one of the rooms with a limited number of students, respecting always the capacity, and it's being recorded and streaming in real time in a set of rooms where we have some other students that are watching these classes via usually Wi-Fi. What is the problem of this? So it is especially the number of connections and the number of transmissions, concurrent transmissions that are demanding this high bit rate and low latency traffic, and what is more, that they need to be concurrently delivered together with the rest of the services and traffic that is present in the network. Moreover, we need to take into account that in these cases, the usually dynamic wireless channel becomes even more dynamic, and that we can observe even different traffic peaks across the entire day. Before all this, we already saw let's say efforts to solve these issues using some other approaches. So on the one hand, we found that the IEEE proposed the 11E amendment in order to improve the real-time multimedia traffic, and although it was a revolutionary advance due to the introduction of quality of service features, the problem is that these features were completely static, and we could not adapt it to the specific scenario or requirements in a specific moment of time. On the other hand, there is existing research proposing QoS differentiation, load balancing, or using SDM principles, as well as leveraging analytical or numerical models from the stochastic and information theory in order to solve these issues. However, although they provide improvements, it has been demonstrated that these solutions are not sufficient anymore, given the increasing number of parameters that we need to tune and adapt in the network, and the greater diversity of requirements of the different types of traffic, applications, and services that have to be held in the network. In this sense, artificial intelligence and machine learning approaches have been used to approximate these complex network optimization functions, showing very good results, especially from deep learning models, which have provided very good accuracy, but that, however, do not provide the insights on how or why a decision was reached. So the problem with this matter is that sometimes understanding the decisions that these models provide are critical. If we talk, for instance, about critical systems based on networks, that it could be autonomous vehicles, it could be e-health systems. But even if that is not the case, understanding this decision contributes to data discovery, diagnosis, and allows expert input, correction, and supervision. So is that the reason why interpretable AI is being every day demanded even more, and that different post hoc models have been and are being proposed in order to kind of translate or try to understand these black boxes models that provide very little information on the reasoning behind them, but that unfortunately until today they are still providing not completely accurate results. In this context, the contribution of this work is threefold. So we first identify which are the requirements and challenges of interpretable AI on the context of wireless networks. Then, based on these requirements, we propose a solution aiming to optimize the channel access in wireless network using natively transparent and interpretable ML models, and we finally demonstrate the effectiveness and the performance of our solution via simulation, taking into account several wireless network metrics. So moving forward to the definition of interpretable AI, we first need to understand the need to have this concept. So the research community and ourselves should make the same question, that is it not enough to simply obtain a correct prediction when we are optimizing a certain feature in a network? The answer is clearly no. Especially in a mission critical system, we cannot trust the reasoning of an NL model that we cannot understand, that we cannot trace back. So that is why it is important to identify what are the main requirements and challenges that we can find in the field of interpretable and explainable AI. But it is also important to define what we mean by interpretable and explainable AI. In the research work, if we go into them, we will realize that usually these two terms are used to refer or to define the same terminology, the same to provide the same definition. But in this work, we actually will follow the same approach, and we will use them interchangeably to refer to the model that produces an output that are intelligible to a human domain expert and that can understand and trace back the reasons to make a certain decision. Based on this definition, we have identified a set of requirements that are mandatory for an AI solution that is used for the delivery of delay-sensitive content in wireless networks. These six requirements are as follows. So first we have identified, of course, low complexity due to two main reasons. So not only because this model have to run in very limited devices in terms of computational resources such as Wi-Fi access points or smart TV, but because the lower the complexity, the easier would be to the network expert to understand the reasoning behind a certain decision. On the other hand, in case that we select a model that have to interchange data to build a more general model trained on different settings, we need to ensure that this interchange is performed without having privacy issues. On the third place, we find the consistency in the sense that the inputs, the relationship between inputs and output of the ML models should be consistent. So this actually would allow easier troubleshooting and intelligibility. In the fourth place, we have transparency. That is, let's say, the inherent requirement for this kind of AI that allows a domain expert to understand the decision and the outputs that have been provided by ML model. In the fifth place, we have the requirements of being able to be simulated and emulated. And by this we mean that especially in a big network, and if we consider an ML model that is taking care of different of the optimization of different parameters, this model has to have the ability to be decomposed and validated first via simulation before reaching real-world stages where they can have greater consequences. So we can isolate the problems that a subsystem can have with respect to other before going to a real network. And six, we have the post hoc analysis that, as I said at the beginning of this presentation, they aim to provide some kind of explanation from black boxes model to be easily readable. So for instance, to understand the sensibility of a certain features. However, we need to keep in mind that inherent transparent models by design do not require this analysis. So based on this requirement, we have identified some of them. We have studied a set of these ML models with respect to the requirements defined before, in order to present an AI solution that has as main objective to adapt the medium access parameters based on the channel access status information and improve in this manner the delivery of delay sensitive content in Wi-Fi networks. In this case, we can see how the requirements stated before are met by two type of models, as they are decision trees or rule-based. There could be other similar, as they could be, for instance, a random forest. But in this case, we have taken as a reference the fact that low complexity is as important as accuracy, and that's an extra reason for the selection of this model beside the fulfillment of the requirements themselves. So based on these two models, we have started a training phase that begins with the collection of the dataset, which is done via simulation. And in here we have designed several scenarios with this distribution of stations. So we identify as defined by the 11E amendment, the stations that do not support quality of service and that are not able to adapt the traffic, the channel access parameters. And then we have the stations that are able to support quality of service and that are able to adapt such parameters. So we can observe how each of them has a different queue and has different access value. So In particular, we will define from highest to lower priority the ones for voice, video, best effort, and background. And these parameters are actually, as I said before, fixed by the standard independently of the channel conditions. So our aim is to improve this delay sensitive delivery by optimizing these parameters. So we have taken in this dataset collection also different aggregated traffic and traffic types. And we have also proposed various alternative combinations to these standard channel access values, always respecting the same priority. So in the case of the AIFS, we have, besides the standard value, provided 10 alternative combinations, among which the ML model can select, and the same for the contention window values. So we can see on the left the one provided by the standard, and the two on the right the one alternative provided by us in this work. We have also identified the most significant features that determine the accuracy of this model, and we have seen for that the global channel utilization, the presence of stations that cannot adapt their channel access parameters, and the channel utilization of each type of traffic. And in particular, the types of models that have been selected have been implemented through the J48 and M5 algorithms, and have been trained in parallel using the same dataset. So, taken as a reference these algorithms, we have proposed a two-phase predicted scheme that is executed in real time 1 per second. So in this image, we can observe actually how this two-phase predicted scheme works. So we first start checking if we have already passed the time by which we can again analyze if we are in optimal conditions, and we retrieve the metrics needed to fit the models. And then we differentiate two different phases. On the first phase, that is, as I said, computed in parallel for the J48 and the M5 model, computes and calculates the optimal AIFS combination that reduces the collisions of the delay-sensitive traffic and allows increasing the performance while respecting the remaining active applications. In the second place, each model takes as a basis the prediction made on the first phase and try to do the same to optimize the size of the contention window. So after this is done, for each execution, what the scheme does is to take the output parameters of the model that achieves the best trade-off between accuracy and throughput, and these values are updated by the access point via beacon frames. And these models can run in real time and can be run in several ways. So they can run directly on access points since they have the channel access information, or they can run on an SD-RAN controller, or even on a ORAN-like architecture on the different control loops. Moreover, in order to reduce the complexity and provide greater transparency, for instance, in the case of the trees, we have reduced the depth of the tree to 3 levels, and in this sense, we allow a networking expert to better read what is going on and what is the decision made in the network. So, for instance, if we have video occupancy more than 30% of the channel utilization, but we have a very great occupancy of the stations that are not able to adapt the channel access parameter, what we have is that the best option is to take the standard values with an error lower than 2%, which would make sense for this experts, since we will have a very big proportion of stations that are not able to do any kind of adaptation. So increasing these values would only harm the performance of the network itself. So we pass now to the performance evaluation, and here we can see all the details on how these scenarios have been designed. We have evaluated it via a simulation using a riverbed modeler, using 100 stations, and an aggregated traffic of ranging from 10 to 22.5 Mbps, leaving the data rate to be selected to the rate control algorithm, and setting also a maximum deadline and from which a certain packet is dropped in order not to increase the delay that the rest of the packets are accumulating, and let's say provide a lower quality of experience for the user. So these values have been set for 10 milliseconds to the voice traffic, and 200 milliseconds for video traffic. And we have evaluated the scenarios with all stations composed of stations with the ability of adapting the channel access parameters, and with stations that also do not support such capability. We first provided the results for the sensitive traffic, so voice and video, and these results are expressed with regard to the standard channel access function. So we are showing the percentage of the gains achieved with respect to the standard. So we can see that for the delivery ratio, we reach up to 60% gain when we have only stations supporting this feature, but that this decreases with the aggregated traffic up to until 20%, a moment where this improvement is the same either if we have this quality of service stations or if we do not have them. This can be also reflected in the reduction of the retransmission ratio, where that we can see that keeps almost constant in around average of 60% when we have all the stations that can adapt to these channel parameters, and that it decrease sequentially when we have both types of stations. And in the last place, we can see the reduction in the percentage of packet drops by reaching this maximum deadline that affects the quality of experience of the user. And we can see how these are very high reductions, so almost around 80% when we have only adaptable stations, and again at the minimum of 20% when we have any kind of stations and the greater traffic in the network. In this figure where we show the network-wide results, we can see how these gains in the sensitive traffic do not only not harm the rest of the traffic, but also is able to improve it. So we can see how the gains in the delivery ratio of the entire network is around 20%, but it is also able to reduce an average of 60% the retransmissions that take place in the network. To finish this presentation, we can conclude that interpretable AI is fundamental to detect components malfunctions and to make informed decisions for all experts and stakeholders. And based on this, we have analyzed the challenges and requirements that interpretable AI have on the delay-sensitive content delivery in wireless network. And finally, based on these requirements, we have proposed a predictive scheme using low complexity and interpretable ML models that are able to enhance the sensitive traffic by up to 60%. As a future work, we aim to tackle the problem using deep learning models and post-hoc models to assess how this part behaves to address the same problem. And we aim to assess the computational complexity and the energy consumed by these algorithms on a real-world testbed beyond only simulations. This is all from my side. Thank you very much for your attention, and if you have any question, I will be very glad to answer them, or you can contact me, of course, by email anytime. Thank you again.